Well, we've made it to the end of Unit 1. This is an introduction to some concepts, terminology that we'll be using throughout the remainder of this course. So let's recap what it is that we discussed in Unit 1. We talked about MOSFET IV characteristics. We just presented them. We introduced some terms like linear region, saturation region, threshold voltage, drain saturation voltage. So some concepts that we need to be familiar with because we're going to be encountering them again and again. MOSFETs are used in digital and analog electronics. The CMOS inverter is the basic building block of digital electronics. So we talked about the CMOS inverter, why voltage gain is necessary to make a CMOS inverter, what controls the speed and power of a digital gate. We introduced some digital device metrics that control the performance of CMOS inverters in digital electronics more generally. We talked a little bit about analog electronics, about the self-gain of a transistor and how the transconductance and capacitance affect the gain bandwidth product of a transistor. So just some key concepts that are important for digital and analog electronics. And we mentioned that there are two types of compact models. The compact model is an analytically simple model for a MOSFET. We're going to be using them in this course for physical insight and understanding of how transistors work. But they're also used, more sophisticated, complex and comprehensive compact models are used for circuit design, and they're the bridge between designers of chips and electronics and the manufacturing and processing people. Okay, let's just quickly summarize some of the key concepts that you should be familiar with after Unit 1. So a MOSFET typically has 3 terminals. There's sometimes a 4th, but it's a different kind of thing. We like to think of a MOSFET as a 2-port device, 2 input terminals and 2 output terminals. And what that means is that one of these 3 terminals has to do double duty. It has to serve as both an input terminal and an output terminal. There are different ways of doing this. The only one that we really discussed was the common source configuration. So the source is common between input and output. So the input voltage we're going to think of as the voltage between the gate and the source. The output voltage we're going to think about as the voltage between the drain and the source. And the drain current is the output current in the output terminal. There are different ways that we can plot and measure and present the IV characteristics. If we fix the drain to source voltage, the output voltage, and if we sweep the input voltage, the gate to source voltage, while we measure the output current, we call that a transfer characteristic. It's the output current as a function of the input voltage at a fixed output voltage VDS. So transfer characteristic, that's a term that you should be familiar with. Now we can also present the IV characteristics as output characteristic. There we fix the input voltage, the gate to source voltage. We sweep the output voltage, the drain to source voltage, while we measure or plot the drain current, the output current. So transfer characteristics, output characteristics, 2 different ways of presenting the IV characteristics of the MOSFET. And you want to be familiar with what these look like. So here are the classic output characteristics of a transistor. IV characteristics like this are useful for making digital and analog circuits. Each of these curves in these output characteristics is for a different gate to source voltage. A fixed gate to source voltage that gets higher and higher as we move up and up. So those are the output characteristics. Output current versus output current. Each of these lines is a fixed input voltage, gate to source voltage. Now, we can define a voltage called the drain saturation voltage, which separates two key regions of this output characteristic: the linear region and the saturation region. And you can see that for voltages bigger than the drain saturation voltage, the current doesn't completely saturate, but it becomes much less dependent on drain to source voltage. Now, we could fix the drain to source voltage, say at a low value, and then we could plot the transfer characteristic. That is, we fix the drain to source voltage, and now we sweep the input voltage while we measure the output current, the drain current. If we do it at a low VDS, we get a curve that looks something like this. If we fix the drain to source voltage at a high drain to source, at a high value, then we could sweep the input voltage and we could get another curve, output current versus gate to source voltage at a high fixed VDS. That's the transfer characteristic. So same transistor, but we're plotting the output characteristics on the left or the transfer characteristics on the right. And you should be familiar with what these terms mean. Now, in the transfer characteristic, you can see that the gate to source voltage has to be at least a minimum value for any significant current to flow. That's called the threshold voltage, and that's an important voltage for a MOSFET. So we've introduced several terms. Drain saturation voltage, when the device is on, separates the linear and saturated region of the IV characteristic. Threshold voltage tells us when significant amounts of current flow. So those are important parameters. Now, MOSFETs can be used in digital electronics, and they can be used in analog electronics. In digital electronics, we're basically using the MOSFET as a switch, on or off. The basic building block of a CMOS gate, or CMOS digital electronics, is the CMOS inverter. And you should be familiar with this inverter. We discussed how its output voltage varies as a function of the input voltage. There are two transistors here. There is an N-channel transistor, for which the threshold voltage is positive. We need to have a gate to source voltage more positive than the threshold voltage for current to flow. And there is a PMOS transistor, for which the threshold voltage is negative. The gate to source voltage needs to be more negative than the negative threshold voltage in order for significant current to flow in the PMOS transistor. It's important to know where the terminals are. For the N-channel transistor, the source is grounded and the drain is connected to the output. For the PMOS transistor, the drain is also connected to the output, but the source is connected to the most positive power supply. So you should be comfortable with this circuit. You should understand why, in the ideal case, the output voltage is a function of the input voltage. Looks like this. This is why we call it an inverter. A low input voltage produces a high output voltage. A high input voltage produces a low output voltage. That's why we call it an inverter. A real device is not ideal. The transition from high output voltage to low output voltage occurs over a narrow voltage range. And you can see that an important characteristic of this circuit is that it displays a noise margin. At the low end, it's not sensitive to the precise value of the low input voltage. We get the same high output voltage. And at the high voltage end, it's not sensitive to the precise value of the high input voltage. We get a low output voltage, the same low output voltage. This is referred to as noise margin. It's critically important so that errors don't accumulate in digital logic. And you can see that it's dependent on having a steep transition between switching between a high output voltage and a low output voltage. The slope of the output voltage in that regime is the voltage gain, if we were to be using this device as an analog circuit. But you can see that we have to have a slope that's at least greater than 1 in magnitude, preferably much greater than 1, in order to have these important noise margins. We also talked about how we switch. If we have a clock, if we have an input signal that is switching between a low value and a high value, then we can switch the output voltage between a low value and a high value. So let's say that the output node is connected to a capacitor. That might be the gates of the next stage. It might be the parasitic capacitances associated with the wires and other things. Well, if we have a low voltage on the input, the NMOS device is turned off, the PMOS device is turned on, connected to the power supply, current flows from the power supply and charges this capacitor up, and we store an energy of 1/2 C VDD squared in the capacitor. Then on the next cycle, when the input signal goes high, the N-channel device turns on, the P-channel device turns off. That energy stored in the capacitor now is dumped to ground through the N-channel transistor. We can estimate the time it takes to put the energy into the capacitor or to pull the charge out of the capacitor. It's simply capacitance times voltage, that's the total charge stored in the capacitor, divided by the on current of the transistor. So current is charge divided by unit time. So this is a simple expression that tells us how long it takes to charge up the capacitor through the PMOS device or discharge the capacitor through the NMOS device. Now, as we're operating at a frequency F, we're charging and discharging this capacitor. We're therefore consuming energy or power. That's the dynamic power. The parameter alpha here is just represents the fraction of the gates on the chip that are switching at any particular time. So dynamic power is important. If we're not switching, one of the two transistors is off. The only current that's flowing is a leakage current. But because there are so many transistors on a modern chip, those leakage currents can add up. We call that the static power. So one of the nice features about a CMOS chip is that an ideal CMOS inverter doesn't dissipate power unless it's switching. In a real device, there will be some static power dissipated when it's not switching due to leakage, and that's more and more important as devices have gotten smaller and smaller, and we put more and more of them on a chip. So the main points that you want to remember about CMOS circuits are that on current controls the speed. Higher on currents mean higher speed. Faster operation, the frequency, means more power dissipated. But it's also important to notice that power, dynamic power, goes as power supply voltage squared. And that's why over the years, power supply voltages just kept going lower and lower until today it's hard to make them go much lower. And finally, you should remember that more leakage currents, when the devices are turned off, they still leak, and that leakage current leads to static power dissipation. Well, we discussed some key figures of merit. On current controls speed, off current controls static power dissipation. The subthreshold swing is important, and DIBL are important. And we talked about what those are. On current, we simply apply the maximum voltage to the gate and the drain. The resulting current in the transistor is the on current, and that's an important number to know for digital electronics. The off current, well, if we have a low voltage on the gate, lower than the threshold voltage, the switch should be off. It isn't completely off. There is some current there. We call that the off current. We'd like that to be as small as possible. Well, the subthreshold swing is an important parameter as well, because we would like this transition from off to on to occur very quickly over a small voltage range. Then we can quickly turn the device on. We can have the device on at a low power supply voltage. Since dynamic power goes as voltage squared, it's helpful to have as low as possible power supply voltage. And that means we'd like this transition between off and on to be as steep as possible. We measure that in a parameter we call the subthreshold swing. We simply ask how much increase in gate voltage does it take to increase the drain current by a factor of 10. Well, that change in gate voltage to produce a factor of 10 change in drain current is called the subthreshold swing, and we typically measure it in millivolts of gate voltage per decade of increase in output current, drain current. And we discussed how. For fundamental reasons that we'll discuss more later in this course, that subthreshold swing for a MOSFET at room temperature has to be 60 millivolts per decade or greater. So the goal of a transistor designer is to get as close to 60 millivolts as possible. Well, another important device metric is called DIBL, and we'll discuss the physics later. It stands for drain-induced barrier lowering. We'll discuss what that all means later in the course. But if we have a plot, on a log plot, so that we can see the leakage currents of drain current versus gate to source voltage, and we do it at a large drain voltage, we'll get a characteristic that looks like this. If we fix the drain to source voltage to be smaller, we'll get a characteristic that looks like this. And you can see that it's translated in gate voltage. If I pick an arbitrary current, a small current, and say I'm going to define my device to be on when I reach that current, you can see that the threshold voltage depends on the drain current. That's an undesirable characteristic of a transistor. We would like the threshold voltage to be independent of the drain voltage. Well, we measure this effect by something called DIBL. We measure the horizontal translation of these two curves. At a fixed drain current, it's the change in gate voltage to give us that same drain current, and we measure the DIBL in millivolts of gate voltage versus volts on the drain, the difference in the drain voltage. So that's DIBL. So those are some important simple device metrics for digital circuits. In analog electronics, we input a small signal and we amplify it. There are a couple of metrics that we discussed, just two very basic metrics, which just are important for analog circuits. So if I build a simple analog amplifier with a very high impedance current source biasing it, then I can ask, what is the gain of this circuit? What is the ratio of the output voltage to the input voltage? And it's relatively easy to show that the gain is minus the transconductance of the transistor times its output resistance. Those are two important figures of merit for analog electronics: transconductance and output resistance. The product of the two we call the self-gain. That's the highest voltage gain that we could get from a simple circuit like this. And it's another important figure of merit. Well, what's the transconductance? Well, if I have a current at some particular gate to source voltage, at a fixed drain to source voltage, if I increase the gate voltage a little bit, I'll get a little bit more current. That change in drain current as a function of a change in gate voltage at a fixed drain voltage, that's called the transconductance, the ratio of those two quantities. So the mathematical definition is the derivative of the drain current with respect to the gate to source voltage, and we can measure it in microsiemens per micrometer or Siemens per meter or whatever our favorite units are. Now, what's the output resistance? Well, at a fixed gate and drain voltage, I'll get a drain current. If I change the drain voltage, but don't change the gate voltage, I will in general get a different current. 1 over the slope of that line is my output resistance. The change in 1 over the change in output current divided by the change in output voltage. So here's the mathematical definition. It scales with the width of the transistor, so we usually measure it. The current is usually given in milliamps per micrometer or some unit like that. So our output resistance is usually quoted in ohm micrometers. We have to divide by the width of the transistor in micrometers to get the actual resistance in ohms. So there are other important device metrics for analog operations, not just transconductance and output resistance and their product or self-gain, but there are other parameters as well. We won't be delving into those in this course. We'll primarily be focused on transconductance and output resistance. Finally, we talked briefly about compact models. So a compact model is an analytically simple set of equations that describe the IV characteristics of a MOSFET. Now, we tried to distinguish between 2 types. In this course, we're going to be using simple, very simple compact models as a way to describe the device in terms of a few very few parameters that have a strong physical significance. We're going to be using this compact model to develop understanding of how the transistor works. Well, this is where our focus is on this course. There's a second type of compact model that is much more involved and has many more parameters that accurately describe transistors of various sizes under various conditions and are used by circuit designers to design the circuits that we all make use of in our electronic products. These are models that are suitable for use in numerical device simulation programs. We'll only be mentioning these kinds of models late in the course. Our focus will be on the simpler models to gain physical insight into the operation of the transistors. But these more sophisticated circuit design models, they are really the connection between the semiconductor manufacturing line and the circuit designers and the product design. So they play an extremely important role for us. All right, those are some concepts that you should try to be familiar with as we leave Unit 1 and move on to Unit 2. Be familiar with the MOSFET IV characteristics and all of the terminology associated with them. Be familiar with how a basic CMOS inverter works, why voltage gain is required, what controls the speed and the power of a digital circuit. Be familiar with some key device metrics that are important for digital electronics. Be familiar with just the 2 key device metrics that are important for analog circuits. And understand that there are 2 different kinds of compact models. The one that we're focusing on in this course for physical insight, understanding how transistors work, the much more sophisticated compact models that circuit designers use to design electronic products. So if you're familiar with those concepts from Unit 2, then we will be ready to move on to the rest of the course. Thank you.